Hello everyone, my name is Pipin Abram and in today's video we are going to talk about total internal reflection. In short, we call it TIR. Very important as far as our boards are concerned. So without wasting any more time, let's get started. Before I come to that topic, let's try to recap what all things we discussed in the previous video. So in the previous video we talked about critical angle. Now what was a critical angle? Imagine we have an interface over here. Here we have a denser medium, here we have rarer medium. Denser media have a refractive index of nu2, rarer media have a refractive index of nu1. So critical angle is that angle of incidence inside your denser medium for which your angle of refraction is basically 90 degree, right? So what is your critical angle? So that angle of incidence inside your denser medium for which your angle of refraction is 90 degree. Basically your refracted ray will be along the surface, right? So this angle of incidence inside your denser medium is what you call as your critical angle. I hope that is understandable. So we all know if we can apply Snell's law at your point A, so that will be very simple, written as nu2 times sine of angle of incidence, that is basically a critical angle, will be equal to nu1 times sine of angle of refraction, that is basically your 90 degree, right? So you can further write this thing as IC is equals to nu1, and if you solve it you will get this particular result. Sine angle of critical angle will be equals to nu1 upon nu2. Is that a yes or no? I hope that is understandable, right? Okay, now a simple exercise. For time being, let us consider our light to be having a wave nature, right? So let's say your light is basically a wave for a time being, right? Okay, so if light is a wave, we all know our visible light is basically made up of 7 different bands of color, which we call as Vibgyor. We have studied this in our lower classes, right? V stands for violet, I stands for indigo, B stands for blue, green, G stands for green, Y stands for yellow, O stands for orange, and R stands for red, right? Okay, great. So if we consider them to be a wave, then definitely they must be having some wavelength, right? Okay, the range of their wavelength is approximately from 4000 angstrom knot to 7000 angstrom knot. Now what is this angstrom knot? Angstrom knot, so 1 angstrom knot is basically equal to 10 to the power minus 10 meter, right? It is very small, right? Obviously we are talking about light, it is basically very small, having very small wavelengths, right? Okay, so you can see if I go in that direction, the wavelength is basically increasing. That means your violet color will be having the lowest wavelength and your red will be having the highest wavelength. I hope that is understandable, right? Okay, now why we are doing this? Because we have a very famous relation which is known as your Cauchy relation. So Cauchy relation relates your wavelength with the refractive index. So in order to study that, we are just trying to consider the wave nature of light, right? Okay, so according to the Cauchy relation, so Cauchy relation goes like this. Your refractive index is actually equals to A plus B upon lambda square plus C upon lambda 4. It's basically a series, right, in which it is D upon lambda times of 6, and this series goes on, right? Now the details are not important. A, B, C, these are all your constant, you don't have to worry about it. If you look very closely, you'll see your refractive index is basically inversely proportional to that of your wavelength. Can you guys see that? Do not go into the details, but from this relation, I can just do a simple estimation that your refractive index is inversely proportional to the wavelength, right? Okay, I hope you guys can get that, right? So what does this mean? This mean that if you have a higher, let's say if you have a higher wavelength, the refractive index for that particular medium will be lower, right? If you have a lower wavelength, the refractive index for that medium will be higher. I hope you guys can understand that, right? So from here you can simply say, from this relation we can say that your nu and your lambda, that is refractive index, and the lambda or wavelength of the wave of the light are inversely related, right? So if it is inversely related, I can simply just make a simple diagram to make you guys understand what this actually means. It actually means, so yeah, you can see, let's say I have a white light which is like made up of all these 7 different bands, right? So if it is made up of different colors, so imagine I have this, let's say this is my denser medium, this is my denser medium, this is my rarer medium. Just to confirm, right? Okay, all right. So let's say you have your violet color coming, right? So like according to this relation, your refractive index is inversely proportional to the wavelength, right? So basically, let's say you have violet color coming, which is having the least wavelength, so it is going to bend very far away from your, from your normal, yes or no, right? So you guys can see the bending will be very far away, right, making a huge angle of refraction, right? On the other hand, for indigo it will be not that huge. Very similarly, for blue it will not be that huge, for green it will not be that huge, for yellow it will not be that huge, for orange it will not be that huge, for red has the maximum wavelength, so it will not deviate much. I hope you guys can understand, right? So you guys can very simply see, for red your angle of deviation is very less, so red color is deviated less. Why it is deviated less? It's pretty simple. If you guys can see this relation, your refractive index is inversely proportional to your wavelength, right? So red one has the maximum, wavelength. That means it will have minimum refractive index, and because of minimum refractive index, the bending will be least. I hope you guys can understand. Very similarly, for violet you have minimum wavelength and the refractive index will be more and the bending will be maximum. I hope you guys can understand. So you guys can see, for violet you have a very huge angle of refraction, right? On the other hand, for red you have a very small angle of refraction, right? Now why I am giving this information to you, because you have to understand in terms of critical angle. So you have to understand, so for this particular, let's say if I talk about a violet light, let's say this is my violet light, right? So violet light, for a very small angle you can see so much of bending, right? So if I increase little bit more angle here, if I increase the angle little bit more, it will reach the critical angle, right? On the other hand, if I want that this red should reach this particular position, that is the critical position, then I have to increase very huge amounts of angle, right? I hope you guys can understand, right? So that means critical angle for violet will be less, will be minimum. On the other hand, critical angle for red color will be maximum. Is that a yes or no? And so does, same trend is followed by all the different colors, right? So I can simply say critical angle for red is the maximum, then comes your orange, then comes your yellow, then comes your green, then comes your blue, then comes your indigo, and the least critical angle will be for your violet color. I hope you guys can understand this relation. Is that a yes or no? I hope this is clear to everyone. Yes? Okay, great. So if that is understandable, let's come to the topic that we are supposed to study today, that is total internal reflection, right? Okay, great. Now we are going to take it further from the critical angle. So you guys can see I have an interface over here, and let's say here we have a denser medium, here we have a rarer medium. All right, great. Now denser medium has a refractive index of ν2, okay, and rarer medium has a refractive index of ν1. Great. So let's say I have a light source over here. Imagine there is a bulb light which is like glowing, right? So if the light ray is going straight, that is perpendicular to the interface, it is going to go undeviated, unrefracted, right? So there will be nothing here, right? Okay, let's say your light ray is going at some angle, right? It hits the interface with some angle with respect to the normal. So there is some angle over here. Let me just draw the angle, right? So there is this angle, let me call this angle 1, right? So for angle 1, what happened? Light ray went, you made the normal there. Obviously we are going from denser to rarer. The light ray will bend away from the normal, right? Okay, great. Then let's say you increase that angle. So you have increased the angle at C, you have increased that angle. Let me just name that angle 2. So the moment you increase the angle, what happened? Your angle of refraction will also increase, right? Now let's say you have increased your angle so much that now you have reached the critical angle. Now you have reached the critical angle. So the moment you reach the critical angle, your angle of refraction will become 90 degree, right? Your refracted ray will be at the surface, right? Now here's the interesting thing. What is going to happen if I increase the angle further, right? Imagine I'm increasing the angle of incidence beyond your critical angle. Now this is where the magic begins, right? Okay, so I have increased my angle of, so this angle is basically, this is basically, let me say this angle IT, right? Total internal reflection. So this IT angle is greater than your critical angle. So what is going to happen, right? Now the next thing that happens is your reflected ray, or I should say the ray is not going to penetrate or go to the other medium. It will reflect back to the same medium following your laws of reflection. This will be reflected back in the same medium, and this phenomena is what you call as your total internal reflection. That means whatever light ray is going, it is not going to go to the other, other, I should say, medium. It is basically reflecting back at the same medium, right? And it will follow your laws of reflection, right? For example, if this angle is 30°, then this angle should also be 30°. The reflected ray should follow your laws of reflection. I hope you guys can understand that, right? So your light ray is totally internally reflected, right? And this phenomena is what you call as your total internal reflection. I hope you guys can understand that, right? So what is the definition says? Definition says when the angle of incidence inside denser medium, you guys can see your angle of incidence inside denser medium exceeds critical angle. Yes, it has exceeded the critical angle. Then the light ray is totally reflected into the same medium. Then the light ray is totally reflected into the same medium. I hope you guys can understand that, right? And this phenomena is what you call, or it's what is known as your total internal reflection, TIR. I hope you guys can understand that, right? Okay, here's a small illustration, small diagram to explain the phenomena here. So you have a common interface here, right? Here above the interface we have rarer medium, below the interface I have a denser medium, right? So what is happening? Yes, here the angle of incidence inside the denser medium is basically lower than the critical angle. So when it is lower than the critical angle, the light ray will go to the another medium, right? Yes or no? Simply it will follow your, basically we are going from denser to rarer medium. Definitely your light ray will bend away from the normal. Is that a yes or no? Very similarly, you have to understand the moment I reach the critical angle, what is going to happen? Your angle, your refracted ray will be at the interface. Your angle of refraction will be 90 degrees. That is yes or no? So we have reached the critical angle. The moment I exceed the value of critical angle inside the denser medium, what is going to happen? The light ray will be reflected back in the same medium, right? And this is what again we call as the total internal reflection. I hope now it is understandable to everyone. Is that a yes or no? Right? Okay, great. So there are a few conditions that is very, very important for TIR to happen, right? TIR will not happen like for all the cases. There are a few conditions which we have to follow so that total internal reflection can happen. Number one, first condition is your light ray must travel from denser to rarer medium. It is just, this is very important, it should travel from denser to rarer medium. So if it is not traveling from denser to rarer medium, TIR will not happen, right? So first condition is light ray must travel from denser to rarer medium. And second condition, which we all know, the angle of incidence that is inside your denser medium should be greater than the critical angle. Then only total internal reflection can happen. I hope you guys can understand. Your angle of incidence inside denser medium should exceed your critical angle. Then only your total internal reflection can happen in the same medium. Otherwise it will go to the other medium. I hope you guys can understand that, right? Okay, so if that is understandable, let's look at some of the data here. So this is a table from your NCERT book. So we have different mediums here. We have water, crown glass, dense flint glass, and diamond. So these are some refractive index here. So water has a refractive index of 1.33, crown glass has a refractive index of 1.52, dense flint glass has a refractive index of 1.62, and diamond has a refractive index of 2.42. So diamond is very dense, you guys can understand, right? It is optically denser than all of the other, right? Okay, great. Now let's look at our critical angles here. For water, critical angle is 48.75. It is approximately 49 degrees critical angle for water. Okay, great. For crown glass, this is the normal glass which we use in most of the substances. So for crown glass, the critical angle is approximately 41 degree, right? Okay, great. Then we have dense flint glass. So for dense flint glass, the critical angle is approximately 37 degrees. And for diamond, critical angle is 24.41. It is very less. You guys can see critical angle for diamond is very less, right? And basically we exploit this property of diamond. You will see in one of the applications of a TIR. All right, well, I hope you guys can understand that, right? Okay, let's look at the applications of TIR. Right now, this is the important thing: applications of total internal reflection. So where these things we see in our daily life, right? Okay, great. Number one, sparkling of diamond, right? Like I was saying. So if you look at the diamond, if I zoom the image, you guys can see there is a lot of cuttings over here. If you guys see clearly, lots and lots of cuttings are there. Can you guys see that? Lots and lots of cutting, and you guys can see it is shining so brightly, right? Okay, great. Now, yeah, so why these cuttings are made, you have to understand. See, these cuttings are made so that so that it can basically shine as much as possible, right? So okay, now let me just very quickly, for example, if you guys see this image over here, and if I try to make you guys understand how the total internal reflection works in diamond. So imagine I have a light ray which is like going like this, right? So you have to understand this. Right now the light ray is going perpendicular to the surface, right? So when it is going perpendicularly, what is going to happen? It will not refract, it will enter the surface, right? Okay, great. So light ray enter the surface, and at this particular point I can make a normal, and the diamonds are cut in such a way that this angle, basically this particular angle exceeds your critical angle, right? And the next part is totally internally reflected, right? Something like that. So basically you guys can see here, if I write it here your your angle of incidence is greater than the critical angle, or it is greater than, we know the angle, it's 24.41, right? So it is greater than 24.41. so because of that, it is totally internally reflected. Again, this process continues, right? Again, this angle is more than your critical angle. Again, this will, if I draw it properly, I hope you guys can see that. Yeah, okay, so it will again exceed something like that. Again, angle, critical angle. So basically what is happening here, it is why this is happening? Because of the cutting that is done. You guys can, which I showed you guys, right? So it will keep on, there will be like multiple total internal reflections, right? Because of that, because of this multiple total internal reflection, what is actually happening? Light ray is entering from this particular place, and light ray is not going out, right? It is like staying here, and it takes some time to go out. Let's say it will go out from some place, right? But it takes some time to go out of the diamond, right? So because of that, whenever we look at the diamond, we see that there is so much light coming out of it. Now what is actually happening? The light is basically kind of trapped inside because of this multiple total internal reflections, like I demonstrated over here. I hope you guys can understand that, right? So because of this multiple total internal reflections, we see the diamond is shining so brightly, but actually what is happening inside, there is light which is like trapped inside, right? That is what actually happening, right? So it does come out, that's why we are able to see, right? So it does come out. So basically before before the light which has entered the diamond will come out, it will basically face multiple total internal reflection, and because of that, we see your diamond is glowing or sparkling, right? So you can see it here, the face of diamond are so cut that the light entering the crystal suffers total internal reflection repeatedly, and hence collected inside, but it comes out only through a few phases, and hence diamond sparkles, right? So like I said, so basically your light ray is kind of trapped inside, and as it comes out, you'll see it is already will be done, already would have done multiple total internal reflections, and because of that, we see your diamond is sparkling like some heavenly being. I hope you guys can understand, right? Okay, next your application is mirage formation. Right now, what is a mirage formation? Is basically an optical illusion. Where do we see this optical illusion? It is observed in desert or over hot extended surfaces. The travelers see a shimmering pond of water some distance ahead of them, in which the surrounding objects like trees etc appear inverted. So basically you must have seen it in movies, cartoon movies, in which some cartoon character will be walking in the desert, and he is seeing an optical illusion of water, and then he suddenly goes and jump off that water, and suddenly he sees that it is just sand, right? So what is this mirage formation? Let's try to understand what actually is happening here. It's basically an optical illusion, right? It is not real, it's an illusion. Now how this illusion is made, let's try to understand this. So for example, imagine this is your desert sand, right? This is your desert sand. So what actually happens is your at summer your desert sand becomes so hot, right, that we will have different layers of hotness over here. So let me just try to make you guys understand. So what actually happens is we will see multiple layers of hotness over here. Let me just make it and I'll just explain it to you what actually happens. So what I'm trying to make here, so normally just like your atmosphere has different layers, right, paddling up. Very similarly here also, the desert, you can simply say this is the sand. So hotness at this particular level will be huge, right, and this particular level it will be relatively less, this will be relatively less, this will be relatively less, this will be relatively less, and here we have maybe colder air, right? So basically your hotness is maximum here, then it will be relatively less, relatively less, relatively less, less and less, right? So basically because of that you can see there is layer kind of formation that happens here, right? So we have to understand your cold air or your cold atmosphere is kind of denser and medium, right? On the other hand, your hot air are rare, because when we talk about hot air, your gas molecules, your water molecules, they go, for example, if you heat something, we all know that if you heat water, it converts into water vapor and just go out, right? But I can simply say the refractive index here is nu1, here it is nu2, here it is nu3, here it is nu4, here it is nu5, here it is nu6. So I can simply write nu1 refractive index term, nu1, nu2 is greater, nu3 is greater, nu4 is greater, nu5 is greater and greater than your nu6, right? So nu1 will be having the lowest, it will be the rarest of all the different mediums, right? So what actually happens is, right, okay, let me just try to make you guys understand. Let's say you want to see this tree from let's say you have your eyes somewhere here and you are seeing this tree, right? So what actually happens, the image of tree, this particular image of tree, it the ray from the tree reaches your first interface, let's say, right? Yes, you will make the normal. So basically what is happening, we are entering from your denser to rarer medium, right? We are entering from denser to rarer medium. So what is going to happen, the light ray is going to bend away from the normal, right? Is that yes or no? It is going to bend away from the normal. Okay, great. Then again we are again entering from, so this will be your denser medium and this will be your rarer medium, right? So we are going from denser to rarer medium. Again light ray will bend away from the normal. I hope you guys can understand, right? Okay, now as it goes from different mediums, you guys can see the angle of incidence. So you have to understand where we are going from denser to rarer medium, right? Denser to rarer medium. So as we are going from your different mediums, your angle of incidence inside your denser medium is keep on getting increasing. Can you guys see that? It is getting increased, right? So there will be one time in which it will increase and will exceed the critical angle. So let's say this is that angle which inside the denser medium it has exceeded your critical angle. So let's say this angle is, let's say, your IT. Basically it has exceeded your critical angle. So if it has exceeded our critical angle, it will be totally internally reflected in that particular medium. I hope you guys can understand that, right? Okay, great. Now what will happen? Now this light ray is trying to go from, yes, this will be its rarer medium, and this is your denser medium, right? So it is going from rarer to denser medium, right? So what is going to happen? Let's very quickly make the normal. So it will bend away from the, sorry, it will bend towards the normal. I hope you guys can understand. Again, it is going from denser to rarer medium. Sorry, it is, yeah, it is going from rarer to denser medium, right? It's going from rarer to denser medium. What is going to happen? Light ray will bend, you know, towards the normal, something like that will happen. And let's say we are watching from here, right? We are watching from here. So when we are watching from here, what is going to happen? So if I extend it backward, you will see your tree is basically inverted, something like that. I hope you guys can understand that, right? Your tree will be something like that. You will see a virtual image of tree, right? I hope you guys can see that, right? So basically what is happening, we will see a inverted image of tree. We will see, or we will, the tree will appear to be inverted, and we'll see, it is basically inside the ground, right? Now, this kind of image we can only see if our brain can imagine if there is some kind of water, and we are basically seeing the reflection of the, this image inside the water, right? So because of this optical, inverted image that we see, our brain assumes, okay, there must be some kind of water. That's why I'm actually seeing this inverted reflection of this tree, right? So again, why this is happening, you guys can understand. This is because of total internal reflection. And why that is happening? Because of the different layers that is formed because of the very, very hot temperature at the desert areas, right? I hope you guys can understand, right? Again, mirage formulation, optical illusion, and this is happening because of total internal reflection. I hope you guys can understand that. Is that a yes or no? Right? Okay, great. Let's move forward to our next application. Yes, this one is your total reflecting prisms, right? Okay, it's very fun. You will love this one. So basically we are playing with your 45, 90 and 45 degree prism, right? So we are going to talk about different cases here. Again, these cases will involve your total internal reflection, right? Okay, now first case, let's look at your first case. To deviate a ray by 90 degrees, right? So if you want to deviate a ray by 90 degree, for example, look at this prism, right? So you guys can see 90 degree, 45 degree, 45 degree, right? And I have this image A, B. So I want to deviate this ray by 90 degree, right? What is going to happen? So let's say your ray is coming perpendicularly here, right? Okay, perpendicularly here, and you guys can see this is perpendicular, right? So that means it is going to enter. No refraction will happen. It will enter like this, right? Okay, so here make the normal. Now the prism is such that, the prism made is such that this angle is actually, more than, so you guys can see, if you understand, a prism has a refractive index of, say, basically it is made up of glass, okay? All right, this prism is basically made up of glass, right? So if it is made up of glass, you guys can see, we actually saw, so glass has a, critical angle of approximately 41 degree, right? So if this, angle is increased, that means it is totally internally reflected, right? So now let's look at here. So yes, so if I zoom this particular thing, right? So you guys can see this is 45 degree, right? If it is 45 degree, this is 90 degree. Yes, so 90, 45, this will automatically become 45 degree, right? Which is basically, so if this is 45 degree, then this must also be 45 degree. I hope you guys can understand. So basically it has exceeded your critical angle limit, right? So as it has exceeded the critical angle limit, what is going to happen? It is totally internally reflected in the same medium. I hope you guys can understand, right? And now you have to understand here, this is perpendicular to the surface, right? So it will come out undeviated, something like this. I hope you guys can see, right? Okay, so your A image will be here. Let me say A dash is the image here. Let's talk about B, right? Again, B will go something like this, right? I hope you guys can understand, right? Again, make make the 90-degree. And again, if you see, this is the thing, right? 90-degree, 45, this will be 45, this will be also 45. That means it has exceeded your critical angle limit. That means it will be totally internally reflected like this, right? And you guys can see it will come out because it is perpendicular, right? It will come out like that. And let's say this is my B dash, right? So if you see clearly, your AB is basically 90-degree deviated, right? So image is 90-degree deviated with the help of this prism. I hope you guys can understand this, right? Okay, great. Let's look at the other one. To invert an image with deviation of rays through 180 degrees. Okay, so you want to invert the image. So let's try to see how we can do that. Okay, all right. So this is your, this is your, your rays will go inside. And again, the same story is going to happen. If you see it here, same story is going to happen. This is 45 degree, this is 90 degree, this is 45 degree, and we can simply make the normal over here. So if I make the normal over here, something like that, so this will also be 45 degree. That means it has exceeded our critical angle limit. So what is going to happen? It is going to deviate something like that. Yes or no? Okay, great. Now what is going to happen? We have to understand that this angle will again be more than your critical angle, and because of that, what is going to happen? It is totally internally reflected again, right? Okay, so it is totally internally reflected, and it will go something like this, something like this. All right, okay, so here I have my A dash, right? Same story is with your B. It will go something like this, totally internally reflected. Again, it will be totally internally reflected. It will come back here, something like this. I hope you guys can understand that, right? Okay, so here you have your B dash, right? So what is actually happening here? If you see clearly, your image is basically inverted. Your image is basically inverted by 180 degree, right? So to invert an image with deviation of rays, your rays is also deviated, and it is deviated by 180 degrees. So for that, you can use this kind of prism. I hope you guys can understand, right? Next one, we have to invert an image without deviation of rays, right? So you want to invert an image, but you don't want the deviation of rays. You do not want your rays to deviate, right? Okay, what is going to happen? So let's say your rays go like here, right? Okay, now you have to understand, here you have you have this is your normal, right? So we are going from rarer to denser medium, right? So when we are going from rarer to denser medium, light ray will bend towards the normal, right? It will bend towards the normal. Let me just draw it again. It will bend towards normal, something like that, right? I hope you guys can see it has bended towards the normal, right? Okay, then this will be more than your critical angle, and because that is totally internally reflected, something like that. Again, we are going basically from denser to rarer medium. That means it is going to bend away from the normal, something like that will happen. I hope you guys can understand, right? Same thing for your B. Again, it is bended towards towards the normal. Again, here it is totally internally reflected, something like that, right? And then again here, so if you make normal, it will bend away, something like that. Here you have your A, and here you have your B, right? Your image is inverted without deviating your rays. I hope you guys can see that. Is that a yes or no? I hope you guys can understand, right? Okay, great. So this was your third application of total internal reflection. Now let's look at the final application, that is your optical fibers. Now optical fibers are one of the revolutionary application of your TIR. Optical fibers are used everywhere. We use it to transmit your audio signals, your video signals. So if you remember, your Wi-Fi LAN cable is basically an optical cable, right? It's basically an optical fiber, right? So optical fiber uses total internal reflection phenomena. the most, right? Okay, now optical fibers are used in transmitting audio and video signals over a long distance. So you guys can see it in the image. So basically your light is going from here, it is transmitted and it is coming out from here, right? And the good thing about this optical transmission is there is no loss of light. All of the light, maximum part of the light come out to the other end, because all of the light is basically totally internally reflected over here. So there is no light which is like going out of your, to the air medium, right? So whatever you go, whatever light you give here, you will get it from here. Anyway, light is traveling with the speed of light, so basically it is very fast. So that's why we use it for your telecommunication purposes, right? Okay, so let's look at what is the working, how this optical cable is basically made. So your optical cable basically had three particular part. So this is what you call as the core. This core is basically made of high quality glass, right? It is basically made up of high quality glass. Then you have an additional layer over here which we call as cladding, right? This cladding is also made up of glass or sometimes plastic, right? But the important thing here is the core is denser as compared to your cladding part, right? So cladding part is made such a way that this will behave as a rarer medium and your core will behave as a denser medium. And then we have a protective coating which we call as buffer coating, so that it can protect this glass. These glass are very delicate to handle, right? So in order to protect it from external damages, we use this very strong buffer coating to cover over it, right? So basically this is the main thing, core. So this is where your reflection happens, total internal reflection happens, right? Okay, so let's try to understand this in your next image. So you have to understand refractive index of new one is greater than your new two, right? So this is important, right? Okay, now if I can very quickly make you guys understand. So this here is your core, right? This is your core, and this very fine line is what you call as your cladding, right? So this is your cladding, right? So you have to understand, let's say your light ray enters. So here we are going from this is your rarer medium, and we are going inside to the denser medium, right? Okay, so it will bend, you guys can see it will bend towards the normal, something like that, and it hits, let's say it hits the interface at this particular point. Now you have to understand, here it is denser, it is going to the rarer medium. So your cladding is your rarer medium, this is your rarer medium, right? Now the optical fibers are made in such a way that every time it hits the cladding or it hits the interface, it is totally internally reflected, right? Okay, great. So this angle, if I try to make this, this what happens, this is more than your critical angle, it totally internally reflected, and the same process happens here, it is totally internally reflected, right? Same process happening here, totally internally reflected, right? Same process happens here, totally internally reflected, right? Same process, totally internally reflected, same process, totally internally reflected. I hope you guys can understand this, totally internally reflected, and it comes out like this. So here we are going from denser to rarer medium, so that means it will bend away from the normal, something like that, right? It will bend, it will come out like that, right? So what actually happens, we are seeing multiple total internal reflection inside your optical fiber. Now this happens at a very rapid speed rate, right? Why it is happening very rapidly? Because light is traveling with the speed of light, right? So but yeah, again we have a medium, so it is not traveling with with the speed of light, but still it is traveling very fast enough, right? So whatever signal that you give it in the form of light, right? Or the Wi-Fi's or the LAN cables, right? The signals, the information signals are in the form of light waves, right? It reaches here and it comes out to the other end without having any kind of lag, right? Very rare lag is there, right? Now that lag is because it is taking some time, but mostly it travels very fast and it can travel at a very large distances. And the important thing is that there is no wastage of signal, right? There is almost no wastage of signal, right? And it can even work if you bend the wire, right? Sometimes we bend the wire, right? But again, there is a limit of bending, right? If you just bend the wire properly, it will crack and the total internal reflection will not work. So that's why we have to be very careful when we are talking about our LAN cables. We have to be very careful. First of all, it is very costly because we are using this technology. It is made up of glass inside, very very fine glasses, right? That's why it is costly. And secondly, you have to maintain it properly. It is very important. If you not maintain it, it will break and this will not work. Again, it's costly. You have to buy a new one, right? So that is how the total internal reflection works in your optical fiber or optical cable that we are using, right? So when the light is incident on one end of the fiber, it goes inside and suffers repeated total internal reflections, right? Okay, even if the fiber is bent, light easily travels through along the fiber. But again, you cannot bend it. If you have made up your mind, no, okay, I will bend it, I will break it, please, if you break it, it will not work, right? Okay, so here you guys can see it's a very good illustration, or it's a very good image of you can see how how your total internal reflection works in your optical fiber. So basically, I'm sure you must have seen this in your decorative lights, because decorative light normally uses this kind of thing. So this is basically made up of plastic fiber kind of material, right? So you guys can see at the end there is this light. You guys can see at the end we will see the light, right? So what actually is happening here, if I zoom it further, your light is actually totally internally reflecting, it is reaching this particular point, right? And at the end we will see these beautiful lights coming out, which we use it as our decorative, for our decorative purposes, right? So this is how total internal reflection have the daily life uses. So we have basically talked about 4 different applications of TIR. Number 1, the first application we talked about was the sparkling of diamond. Second application was your mirage formation, that we see it in the desert, right? Or a place where over a hot extended surfaces, right? Normally if you are living near Rajasthan area or near Jaipur, you will actually see it in the roads also, right? You will actually see it in very very summertime. For example, the temperature is around 40, 45, maybe 50, right? At that particular time you will actually see that there is water nearby in the road also. You can actually experience that if you are in Jaipur or northern area where the summer hits really hard, right? Okay, so next one is your totally reflecting prism, right? So we can use different kinds of prism to get our images according to our will, right? Then we have optical fibers, our Wi-Fi cables, our LAN cables, right? We are using this to transmit our audios and video signals for a very long distances, right? So we talked about this, right? So that was all. We talked about total internal reflection. I hope you understood this concept. If you have any doubt, you can comment it down in the comment section. That's all for today. Thank you and have a nice